What's going on, math people? Today we're going to be talking about continuity. All right? Continuity. So, all right, let's just do a real quick little something. I want you to follow with me right quick, right? All right. Root word in continuity. Continue, continuousness. All right, so let's assume we got us a nice little room, you know. Put some wheels on that thing. Oh, and we burning rubber, baby. Everything's going. And it takes off. And then get right there. And then, boom, there's a gap right there. That open space. That means there's danger happening right there, right? Danger, 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 danger. Right there is no longer continuous. And that's all we're focusing on right now, continuity. Where is it going to be continuous? All right. So going through this whole continuity standpoint, and also what I want you to notice, that is on the horizontal plane right there. And on the horizontal plane, that is the x-axis. So continuity is referring to, it's built from values off of the x-axis. All right. So now let's make it look more mathy. All right. We got a Cartesian plane. All right. And on this, we have -1, -2, -3, and so on, +1, +2, +3, and so on. All right. Give me a color. I will take blue. And let's say we have this happening right here. All right. So let's do some crazy stuff. Really throw this thing all out there. All right. And we'll call that +5. All right. So my question is, here's my question. We got this layout. We have our blue graph there. And first of all, this function, is it continuous everywhere? Continuous everywhere. No. Continuous everywhere? No. Why not? And the answer why to why not is because, first of all, it has an endpoint at -3. That's one reason. It has an endpoint at -3. So it's not going to go to -infinity. The second part of why not, it has a gap at +2. So it's not continuous everywhere. All right. Now here's my other question. All right. Is it continuous? Is it continuous on the interval and on the interval from continuous on the interval -3 to 0? Well, how do you determine that? I'm glad you asked. You would jump right out there. You go to your graph starting at the x value of -3, and you go ahead and you trace that graph until you get to the x value of 0, and you notice you have no gaps. So that little car we was rolling up with, that thing went all the way through -3 to 0. So the answer to that is yes. It is continuous from -3 to 0. All right. Now, here comes a tricky one. is a continuous from 0 to positive 3. Continue continuity from 0 to positive 3. I hope you said no, because you got that big whopping gap right there. You're probably saying, what is that? What's going on with that blue dot right there? So here's the thing. It's not continuous from 0 to 3, but it still has a value at that 2. So you have, and let's call this function, just call it function f of x. So we have f of 2 equals, you go to the dot, you go to that dot, and point, that dot is telling you f of 2 is equal to 5. Awesomeness. Alright, so we've been playing with some little drawings and whatnot, so we need to also look at this from another standpoint. Let's get more calculated, if that's a word. Look at it like some calculus talk. Alright, so example. Alright, so we have our example here. Let's draw another plane, and let's say we have something that looked like this, and we're going to get our handy dandy little eraser, and I want to put a gap right there. Boom. I'm going to put a gap on the end. Alright, thank you. Once we got our gaps, alright, as a matter of fact, let's toss another gap right there at the origin. Boom. Alright, so we have our gaps, and let's put some numbers to show some respect. Put some respect on my gap. Alright, we'll just say that's 10, and we'll say that this is on the x-axis, this is 2, and here is 4, and at the origin there is 0. And let's put in some more craziness, right? Let's toss a dot up here and bust a nice little gap right there. Boom. Alright, so we have some things going on. Alright, and we'll call this 20. Alright, so we have all this stuff happening with the graph, and we're like, okay, what is the issue? The issue that we're trying to find out is, first of all, what value would make our function f of x continuous at and we'll say continuous at 2. Continuous at x equal 2. What value will make our function continuous at x equal 2? Right now, the function is not continuous at x equal 2. You see that gap right there at x equal 2. So what we'll do is we'll look at it from a calculus standpoint of limits. So let's say the limit of f of x as x approaches 2 from the left equals I'm sorry, I had a little brain fart. So we're coming from the left. So I'm going to get right there to the left of it. And what do I get to? That limit from the left, we pull out with a value of 10. And that's supposed to be a pencil. Value of 10 from the left. And then the limit as x approaches 2 from the right for the function. Alright, so we're going to come from the right and go to the right of 2, head back towards 2. From the right also has a value of 10. So the value that will make f of x continuous at x equal 2 is 10. Because we went to the same location from the left and from the right. Alright. Dun 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 dun. Alright, so sometimes you'll be given equations or functions and it say determine if the function is continuous. That takes you straight back to algebra. Alright? Going straight back to algebra. So let's say we have f of x equal to 7 over x minus 14x minus 9x. So we have a rational function combined with a linear function. Now, we know that the domain of all linear functions is all real numbers. So we don't have to give negative 9x any of our energy. And we also know from college algebra, in order to find the domain of a rational function, this is just a complete general setup for a rational function, we take the denominator. The domain is calculated by taking the denominator and setting it not equal to 0 and then solving for the variable. Here's the thing. If it's not in the domain, that value is the value that makes the function discontinuous. Alright, so let's see here. It says determine the point at which the given function is continuous. Alright, so we want to find out what the domain is. Alright, so we're going to go ahead and look at the rational function piece. We're going to take that denominator, set it not equal to 0. X minus 14x cannot equal to 0. I'm going to factor x out of both terms there. I have, hold up, there should not be an x right here. That should just be 14. This guy tripping. Alright, so x cannot equal 14. So that simply means the domain is every number, every real number, excluding positive 14. We put in parentheses on that 14 because that says do not include that value. So we have every real number excluding 14. Then we just wrote it out in interval notation. Alright, so this function is continuous everywhere in this domain. Take that 14 out. So it's rolling, rolling, rolling. Alright. And you know, we're making progress. We're making progress. Alright, just another algebra recap for continuity. Let's say you have an even root radical. Square root of 5x minus 20. And you want to find where it's continuous. It's continuous everywhere in its domain. And we know for even root radicals, in order to find the domain of an even root radical, you take the expression, the domain, you take the expression and set it greater than or equal to 0. So in our case, the expression is 5x minus 20. So we're finding the domain. And we're going to set that expression greater than or equal to 0. And booyah. Solving, you good people. Have your domain there. So this function is continuous everywhere on the interval 4 to positive infinity. All right. Ba-da-ba-ba-bow. Just like that. And that, my friends, is where you and I will call it to a close. All right, my math people, see you next time.